This is chapter 2, motion in a straight line. Now, a matter having a finite size, shape, and occupying some definite space is called as a body. Change in position of an object with time is known as motion. So we have defined the word body or an object and its motion. An object is said to be at rest if its position does not change with time with respect to a reference point that is generally stationary or with respect to its surrounding objects. Now, we are going to define the word motion. Motion of a body can be of three types: rectilinear motion, the translatory motion, or circular or rotatory motion, and oscillatory or vibratory motion. So we have discussed three types of motion here. Rectilinear motion is that motion in which a particle or a point mass moves along a straight line. If a particle or point body moves on a circle, such a motion is called as a circular motion. If an object is small enough so that we can treat it similar to a point, we call such an object as a point object or a point particle. A frame of reference is a set of coordinate axes in terms of which position of an object with reference to which physical laws may be mathematically stated. I repeat this. A frame of reference is a set of coordinate axes in terms of which position of an object with reference to which physical laws may be mathematically stated. Position vector describes the instantaneous position of a particle with respect to the chosen frame of reference. Then we go on to define distance, displacement, velocity, average velocity, and average speed. These are the 5 things we are going to define here. Try to understand them completely. Distance is a measure of the length of the path taken during the change in position of an object. Distance is a scalar quantity, it does not specify direction. Whereas displacement is a measure of the change in position of an object, the displacement is a vector quantity and it has a certain direction. For example, going from A to B is not the same thing as going from B to A. The total distance may be the same, but the directions are different. The rate of change of position with time is known as velocity. It's a vector quantity whose magnitude is simply the speed of the particle. It's a vector quantity because it is the difference of two displacements. The average velocity of a moving particle over a certain time interval is defined as the displacement per unit time. So I'm going to take the displacement and divide it by the time over which that displacement has taken place. Average speed, which is a scalar quantity, is expressed as average speed is equal to distance by time interval. Distance by time interval. Then in this frame we'll discuss instantaneous velocity, acceleration, average acceleration. These are the quantities we are going to describe. The velocity at a particular instant of time is known as instantaneous velocity. It is pertaining to that instant only. Acceleration is the rate of change of velocity with time for a moving particle. So this is first of all we are explaining what is acceleration. It's the rate of change of velocity. Now we have two kinds of accelerations. One is average acceleration, the other is instantaneous acceleration, similar to the velocity. The average acceleration for a finite time interval is defined as average acceleration, which is written as average acceleration is change in velocity during the time interval divided by the time interval. Average acceleration is a vector quantity whose direction is same as that of the change in velocity. That is, A average is delta V bar divided by delta T. Okay. Now point 19, the acceleration at a given instant of time is the instantaneous acceleration. It will have one unique value. If the speed of an object remains constant, then the motion is called uniform motion, and if the speed is a variable, then motion is called as a non-uniform motion. Point 21. The position time graph for uniform motion is shown in figure 2.1. Notice that here we have plotted time on x-axis and position on y-axis, and V is the slope of the graph of this graph, which is this distance divided by this distance, that is x2 minus x1 divided by t minus t. At time t equal to 0, you have the value of of position as x1, and as time increases from here to here, the position increases from x1 to x2. So my equation is x2 equal to x1 plus vt minus t, where v is the slope of the graph, which is supposed to be constant for this purpose. Then instantaneous velocity is defined as the rate of change of displacement. The velocity time graph for non-uniform motion is shown here. Notice in the case of uniform motion, I had a straight line going up or coming down. But here I have a line which is curved. That is, at every point, its slope continues to change like this. So when I plot time against velocity, I get this velocity time graph for non-uniform motion. At t1, the velocity is v1, and at t2, the velocity is v2. Now, the distance traveled in nth second, that is, notice that this is not the same thing as distance traveled in n seconds. This is nth second, in 1 second, is given by xn equal to v0 plus a by 2 to n minus 1, where v0 is the initial velocity, a is the uniform acceleration, and x0 is the distance traveled in the, xn is the distance traveled in the nth second. So this is the equation for that purpose. Then the velocity time graph 2.3 gives the three types of information. We have plotted time on x-axis and velocity on the y-axis and claim that there are three informations you have in it. The instantaneous velocity, the slope of the tangent to the curve at any point, gives instantaneous acceleration a equal to dv by dt. Instantaneous velocity means at a given instant t1, what is the velocity is what is given here, t1 v1, t2 v2. And second information is the slope of the tangent. So now if I draw a tangent here like this, then the slope is nothing but tan theta, where theta is the angle made by the tangent to the x-axis, positive x-axis. Then third is the area under the curve, this whole area covered by the two ordinates and the x-axis and the curve itself. This whole area is nothing but the integral of integral equal to v integral dt1 to t2 dt, and it represents the area under the curve, giving us the total displacement of the particle. Then comes this. For a freely falling object, the three equations of motion are v equal to v0 plus at, v square equal to v0 square plus 2ax, and x equal to v0 t plus half at squared. Now, if this is freely falling under the gravity, then a will change to plus g, and if it is object is thrown up, then a will change to minus g, where x is the displacement of the body and v0 is the initial velocity of the projection in the vertical downward direction. However, if an object is projected vertically upward with initial velocity v0, the equation of motions are v equal to v0 minus at, that is, a will be replaced by g. V square will be equal to v0 square minus 2ax, the a will be replaced by g again, and x equal to v0 t minus half of at square, a replaced by g. The velocity with which an object moves with respect to another object is known as the relative velocity of that object. See, here we are talking about velocity of one with respect to the other, and that is where the concept of relative velocity comes into the picture. So with this, now we will go on to the important formulae of this particular chapter. Okay, this is chapter 2, motion in a straight line. We are continuing. Now, these are the important formulae. Important formulae are these. For one-dimensional motion, the displacement delta x is the difference between two vectors x and x naught. Delta x is x minus x naught. Average velocity is defined as the ratio of the displacement of the object to the time interval. So I'll say delta x over delta t, v average, x2 minus x1 divided by x2 by t2 minus t1. Then we have the average speed involves total distance covered and is independent of direction. It is given by the relation S average is equal to total distance divided by delta t. Notice that it has no direction. Instantaneous velocity, however, will have a direction, which we are going to define in style as v equal to limit delta x by delta t as delta t tends to 0, which is also written as dx dt in calculus. Basically, this is the calculus notation. The equations of motion for constant acceleration A are as follows. First equation is v equal to v naught plus at, which follows from the definition of acceleration that it is v minus v naught divided by the time taken. Then comes the displacement, that is x minus x naught, effective total displacement in time t. X minus x naught is v naught t plus half a naught square, where v naught is the initial velocity. A is the acceleration. Then the next equation is v square. V square, actually square is not written here, by mistake it is slipped. V square equal to v naught square plus 2a x minus x naught. That is the definition here. Then you have x minus x naught equal to half v naught plus v into t. That is simple the displacement over a time t when the velocity changes from v naught to v. Then x minus x naught is also written as vt minus half at square in case my acceleration is negative. For a freely falling body, the acceleration a is equal to minus g, and for an object going up, we will consider it as plus g by definition. So this is the... Okay. Two trains take 3 seconds to pass one another while going in the opposite direction, but only 2.5 seconds if the speed of one is increased by 50%. The time one would take to pass the other when going in the same direction at the original speed is what is required. Now, my solution is going to be something like this. We are talking about relative motion between two trains. So, T is equal to d over Vr, where Vr is the relative motion. If V1 is the speed of the first train and V2 is that of the second train, now if I increase the speed of V1 by 1.5 times, then my change is going to be this. So 3 minutes equal to d over V1 plus V2, and 2.5 is equal to d over 1.5 V1 plus V2. Here I have got 3 unknowns and 2 equations. So by elimination I am getting V1 as 2d by 15 and V2 as d by 5. When they are going in the same direction, notice that I am interested in when they go in the same direction, Vr will be V2 minus V1. That is d by 5 minus 2d by 15 multiplying by 3, I get d by 15. And ultimately what I am interested is when they are going in the same direction, what is the time taken to cross through. That is going to be d over Vr. So d over d by 15, that is equal to 15 seconds. D will cancel out itself. So that is the answer for this equation. Now let's go to the next equation. Now this is problem 19. This problem 19, 4 particles A, B, C, D are in motion. The velocities of one with respect to the other are given as these. They are given as 3 relative velocities, and we are required to find the 4th relative velocity. VDC is nothing but VD minus VC, 20 meters per second towards north. VBC is 20 meters per second towards east, and VBA is 20 meters per second towards south. I'm interested in the relative velocity VDA, and these are the options: 20 meters or equation towards north, towards south, towards east, towards west. Our equation is going to be like this. Supposing they are going in different directions, we take east, north, south, and west normal situation in problem 2.5. You see that VDC is VD minus VC, that is 20 to the north. This is VBC is VB minus VC is 20 to the east, and VBA is VB minus VA minus 20 Z to the, this means to the south. Now if I name these equations as 1, 2 and 3, and if I take 1 minus 2 plus 3 by observation, you will see that VD minus VC minus VB minus VC minus VB plus VB minus VA. If I write VC, VCs and VB will cancel, giving me VD minus VC, and that turns out to be 20Z minus 20I minus 20Z. So these two cancel, giving me minus 20I. Now if I is positive x direction, obviously minus I is going to be minus, so that is, if I is eastward, minus I is going to be westward. So my answer is 20 meters per second in the westward direction. That is the answer, 20 meters per second towards west. That is the answer is D in this situation.